Hello everyone, welcome back. In this video we're going to be talking about allylic halogenation of your radical processes. So let's just dive right on in. Okay, so if we look at an allylic system, we're going to see that when we undergo a radical process, we have the possibility of forming a new carbon-halogen bond at the carbon adjacent to the double bond. Right? It's the allylic position. So let's walk through this process and explain why this happens in the site that it has, or why it has the selectivity, regioselectivity that it does. So just for fun, we haven't been through this in a while. Initiation, right? Remember that in all cases, when you are doing a homolytic cleavage, you have two arrows, one for each electron in a bond to make two radicals. Next step up is propagation. So here we are going to generate our carbon radical by abstracting a hydrogen. So here we have three arrows, one coming from the radical and two addressed by the carbon-hydrogen bond. This forms a carbon radical and an HX bond. Now this radical is stabilized through resonance. Right, so we can resonate through radical processes to form a sharing of the, to indicate a sharing of the radical across the two terminal carbons shown here. Right, so resonance. So this is a resonance stabilized radical. That's why you're going to form it at the carbon adjacent to the carbon double bond. All right. So that gives you your selectivity. Again, where you form the radical indicates where you are likely to halogenate. And we'll go over that in a little bit. So next step in our propagation involves three arrows, one coming from the radical and the carbon to form a new bond with one of the halogens, generating a new halogen radical. And finally, after that, so now we've formed our desired product. That will continue on, this radical will continue on through more propagation steps. And we will get the next step in this, after we've kind of consumed all of the radicals, will be termination. So here we have X coming together with either one of these carbon radicals to form more of the product. You could have the radicals coming together to give you starting material, or in some cases you could have both of the allylic radicals coming together to form carbon-carbon bonds. All right, so there are the general steps in radical halogenation again, and how it works with an allylic system. So now let's look at the conditions for this. All right, so there are some specific things that we have to consider when looking at allylic radicals and radical reactions occurring in the presence of double bonds. and this is true for all halogens. We'll just use Br2 really example. So we generally use Br2, one because of selectivity, but here we'll see the ideal reaction would be the one shown here, right? Where we would get all of our starting material converted to this product. However, what we do also see in these conditions is the formation of this product as well. So we get a mixture of these two products, one where we get the radical reaction, another where the bromine adds across the double bond. Right? So here we see this product, which comes from a competing electrophilic addition reaction. Right, so you don't have to necessarily know the mechanism of this. I'll show you really quickly just how this happens. We'll get into electrophilic additions in the next course. So remember, double bonds are electron rich. You can end up forming this bromonium ion, which is then attacked by the bromine anion to give you your brominated species. Right? So in general, we don't want this to happen. So how do we prevent this from actually occurring? Well, in order to do that, we have to consider the reaction conditions. Now remember, here we've used bromine in either heat or light to initiate our radical process and to halogenate. And as a result, the same reaction conditions allow it to add across a double bond. So is there potentially another reagent that we can use? Well, in looking at this, really the key to preventing this side reaction we need a low concentration of our halogen. So instead of using Br2, which we're going to have to use in at least equimolar amounts, we can employ a different reagent in bromosuccinimide, which I'll draw here, that allows for only slow release of bromine. So this in light undergoes homolytic cleavage to form small amounts of our bromine radical. So if we look at how this works in a reaction, and I'll mention that NBS is poorly soluble in a lot of things. But will actually work. What you'll end up getting from this is your desired product in roughly 85% yield and succinimide. So this allows you to selectively produce the radical halogenation product and not the electrophilic addition process. So anytime you see a double bond in your reactant and you're wanting to do a halogenation at an allylic site, what you want to use is the N-bromosuccinimide, or you can even try N-chlorosuccinimide, but generally NBS is the most common reagent. All right, so that's the end of allylic halogenation. If you have any questions, come talk to us in office hours.